All right, for this class, we have an assignment due Wednesday. I'll get the last assignment to you and the last project to you. We're probably a couple days out now from covering the content for the last project. So between that and exam 3 and exam 4, that's basically it for what we have left of the class. We're getting there. We're actually quite close. Last time we talked about parsing in a bit more detail, so this was an example parse that we did. But now we're going to get into the building of the parse tree for this program. So we've worked on a context-free grammar, and take note of this grammar or close to this grammar. It's okay to just leave expression as an expression without further definition at this point, because we are going to look into generating this program with the parse tree. So let's go do it. So here's how we might start. But let's actually fully draw out the program via a sequence of replacements. And you can do this either from continuing this on or from a parse tree form. So let's start there. Give you a couple minutes and I'll get back for those of you who haven't written this down, go ahead and write down just the program. All you have to generate is main, open parentheses, close parentheses, a equals 4, b equals 8, print a plus b, with the associated grammar that we have there. Give a little bit of time for this, and then think about actually generating that program.
This one specifically, or just anything?
Yeah, this specific program. So utilizing productions of the grammar, be able to produce the associated parse tree. And obviously we don't have anything for a equals 4, b equals 8, but leave them in their non-terminal forms, like variable equals integer is kind of the terminal point for that, where we don't have the variable is a, etc. But if you're doing a parse tree, then you could fill that out. So we would have hopefully this is starting to feel a bit more like review. Like we've done this and seen this before.
Appreciate the signal providing, so that'd be hard.
It's always the case, right?
And I'm pretty
It's
sure
like a
since
roller
it's 6
coaster.
over, it's gonna get hard.
It's a roller coaster, up and down and up and down and up and down. Yeah, parse tree ends up looking something like this. And we have talked about this before, but how do we traverse this parse tree? How would we reconstruct the program from the parse tree? Depth first search, which is the equivalent of a pre-order traversal. All right, so yes, indeed, this is exactly what the parsing step of a compiler does. And this seems very familiar because we focused a lot on this part of the compilation process this quarter. So once we have this parse tree, then we pass this parse tree on to the type checker, because nothing about this parse tree tells us whether there is any semantic meaning here. You can see that we would have tokens for something like assign B hello. And all we have the ability for variables to store in this grammar are integers. So there is no string, there's nothing that is a string variable or anything that could reasonably do this. And syntactically, we would represent hello, we would recognize that as a token. We just don't know if that is a variable name or it doesn't have something, it would be the next token that goes there. And so syntactically, it works, but semantically, it does not. So type checker will look for semantic errors. It's a two-part process. One of them is, it's kind of a meet in the middle. One is going to go top down and look for what types are we expecting, and another is going to go bottom up and say what types are we producing. And then we will try to meet in the middle and say, when we have an assignment, is the left-hand side of that assignment the same type as the right-hand side of that assignment? The left-hand side will be the expected, the right-hand side will be the actual. And at every point that we could possibly meet there, we're going to be looking for some kind of agreement. And we'll see that when we do find semantic errors, sometimes we can handle them, but oftentimes we cannot. In Java, for instance, there may be a type clash when we try to assign an integer to a double, but that is something that is defined within Java's grammar. So there is an out for this. We can convert the integer to its associated double representation and store it in the double variable. Whereas if we try to do something like int equals string, then there is no such ability to do that. So we would have to force compilation to halt because there's no default interpretation of that behavior. The user has not given us something that we have one and only one way of handling. So we do not want to assume what the user wanted. We have to force them to correct the mistake before they attempt to recompile again. And we can see now why it's important to do this, because when you compile a program and it tells you I was successful, there should only be one possible program that comes of that. So here's almost exactly that. Takes an int and a float, method is passed an int and a string. Yeah. Sometimes there are built-in functions for handling them, sometimes there are not. So an int and an int we can handle in Java, but an int and a string we could not for a method that takes an int and a float. This depends compiler to compiler, and if you're writing your own compiler, you will have to make design decisions about when to do this and when to not. Is there a reasonable way to convert from one type to another, and is that what the user intended? If a user is coming from another language and just makes an assumption that your compiler can do something, is that the way that you are handling it? You don't want to insert confusion into your compiler. Of course, just like any program, there should be an API for it. So intermediate code is going to go through the derivation tree and find some intermediate code representation for it. What usually happens in this process is we're looking for either simpler or faster code. In general, we're trying to map this onto more of an assembly style of operation, where instead of allowing for arbitrarily complicated expressions or arbitrarily complicated statements, we would say each statement should only utilize at most 3 memory addresses. And that means that we can map them onto registers, which means that we can now utilize and map this to an assembly instruction. So as an example, it would turn something like this code into that code. Take a second, convince yourself this is equivalent. Is there always a way to do this?
I would hope so. It's mapped from the, it's one of our grammars where we have like only non-terminal, we restrict the number of non-terminals to the right side to 2.
Yeah,
Just chop it off and make more production.
yeah. So that would work if it's always the same operation. So what if there are some additions, some multiplications, some divisions, some exponentiation? What if some of that on the other side is a bit shift, or and at the end of that you have an assignment?
Well, you just, as long as you make sure that your usage of temporary variables matches the order of operations, right?
Yes.
It's the,
Yeah, there's always a way to do this, and that's by design, so that we can, at the intermediate code step of a compiler, be able to map them directly onto what we need to convert to. If there was not a way to do that, then this process would be impossible. And we need it to be possible because the end goal of any higher level programming language is to be convertible into a lower level language. So it's a very interesting thing to note that that is a restriction that we place on every language that we make. Even if it's something that's non-object oriented. If you've seen a functional language and you have the ability to pass functions into functions as parameters and return functions from functions, it still works that way. It's just a separate order of operations. Once we have this intermediate code that maps more directly onto assembly instructions, we can optimize. We find frequently that intermediate code that is generated is suboptimal in nature. There are unnecessary operations in there, or we can reuse variables. We can reuse, there's something that allows us to map this onto something more efficient. So with a pass, a code optimizer will look for viable optimizations. The question I would have for you now is, can we optimize the code on the prior slide? So I'll let you stare at this, the into for statement. What can we do? Yeah,
Can't you just reuse temp 1 instead of temp 2?
Yeah.
It's the same operation.
yeah. So we find ourselves redoing something, yeah,
If A, B, or C or D are constant, they can be merged into one. During the
okay,
process.
yeah, if they ended up having the same value,
Or not the same value, but the same type.
okay, the same type, so if they're integer and integer, you mean?
Yeah, so that way that it's the addition wouldn't have to be done at one time.
Okay,
you could use the same location of A or B for your temp variable too.
So. For the moment, we'll just talk about one of those, which is just that we can reuse the sum of A and B, store that and look it up, and frequently that is the case where anytime that you would do repeated work, you just cache it and then refer to the cached value rather than recompute. But there are many other types of optimization, as mentioned, especially from those of you who have taken architecture or OS courses, which should be most of you at this point. There are lots of optimizations that can be done. The goal of the code optimizer is to do those optimizations. And on the other end of this, we end up with some kind of assembly or bytecode or machine code, whatever the target language of the compiler is. So temp1 equals A plus B might map to some assembly instructions, moving into registers, math operation between registers, move the result back into a variable from those registers. So yeah, the goal at the very end of this is that they map directly onto the target language. So a very brief overview of exactly what those steps are and how they work, but there are a few other pieces to a compiler that might be worth just going over. What extra structures are they using? These are the algorithms and the sequence of algorithms, but what else do they need in order to store what they do? The first one is a symbol table. Whenever we generate a new identifier, so we make a new variable, we define a new function of some kind, those names have some purpose. And they're also not known until we're analyzing the program. It's not like a keyword that is based on the language. While always has the same meaning. But if I make a variable named A, then there is a mapping between the user's desire to know what is currently stored by A or to modify what is currently stored by A. We need to have some way to access that variable. So that is called a symbol table. Just stores, it's a map of symbol name or identifier name and identifier value. So as part of the scanning process, we recognize those identifiers and then we add them to the symbol table. Once we get to the parsing step, we're able to figure out what their associated variable types are. So then we can create the actual map between the type of variable and the name. In the type checking phase, we refer to the table to make sure that what is expected is what is there. How do we know what is there? Well, let's look up into the symbol table. So the symbol table is used throughout. Just a way of storing identifiers. There's also error checking. So when we scan, there may be some particular string that does not match a valid token type, which may cause us to have to crash and report an error. In parsing, there may be some sequence of tokens that don't match a production, in which case we have no ability for the language's grammar to actually produce program. And it would be nice if we could do something intelligent when we do find an error. Record some kind of important information about it, report that back to the user. The best compilers that we've used always report something about what line number it occurred on, what the actual error was, something that allows the user a good chance of being able to identify and fix whatever happened. It is not the compiler's job to attempt to fix that or to try to interpret the error. It is always identify it, return it to the user, make them deal with it. Which you tell that to a 210 student and they say, well, why not? Why can't it just fix it for me? They know what I meant.
Right.
Which when you're actually writing the compiler, no, you do not want to interpret what they mean. you don't necessarily know what they intend, and if a compiler is doing something like that, run, never use it again.
Well, I mean, that's basically what people want vibe coding to be.
Right?
It's like ChatGPT, just do what I want. Just make it do what I want.
This ad on YouTube, like base 64 or base 44.
Mm-hmm.
We're getting to a point where you don't need to learn how to code. Nah, we're gonna kill that guy.
Gosh.
Just wait,
Those
in
special
4 years,
Right.
in 4 years, I'm gonna have students who say exactly the opposite. You're the last of your generation. You're the last sane students I'm ever going to have.
We're gonna put it like
I think actually,
that.
now I know how, James Ludd felt.
Yeah, oh yeah.
If you ever, he was the leader of the Luddites, the original Luddites. In modern times, Luddite means someone who just likes technology, but he was against the automation of the stuff that he was doing.
Yeah, I've heard of Ludditism.
Also,
Yeah,
it also doesn't help that the base 44 guy has the most punchable face in the world.
Okay, so I'm not alone, let's make sure.
alright, what is this?
All right, so from this overall compiler process, the unfortunate reality of a 10-week course is that we can't do justice to every single step of this process. So we've been talking about parsing. And so I want to identify, parsing is one of the most challenging steps of the compiler. I want to zoom in and really focus on not only how do we parse in general, but how can we improve parsing to be as efficient as we possibly can. What differentiates a program that we can parse efficiently from a program that we can't?
And that's this, it's kind of the big, difference between programming languages, like how they can parsing and stuff.
Yeah.
It's like the big question.
Yeah, a lot of tokenizing is very consistent across languages. It's just how you interpret those tokens that varies. But yeah, parsing makes a very big difference. And so knowing some of the parsing theory will help to be able to determine when can you write an efficient compiler, an efficient parser within a compiler. How do you parse in linear time? Because we've seen CYK, we've now implemented CYK. So we know how to do this in general in qubit time, but is there a potential speed up for this? And to do this, we really have to talk about parsing in general for a bit, and then we will talk about how to analyze parsing at a highest level. That becomes one of the, again, more challenging things that we do in the class. But we have it easy for about one more day. Okay. I just feel like I've got this ominous power that it feels like Palpatine. It's kind of addicting. So motivation is pretty straightforward. We know a good bit about parsing so far. But maybe we can summarize what we have seen so far with regards to parsing. What did we try and what have we seen? So we saw two major types of parsing. One that was an absolutely garbage idea and one that became a programming project. What was the garbage idea?
Those are street parsing. It's like parsing every possible derivation tree.
Yeah, looking brute force at every possibility. And what was the runtime of brute force parsing? It was exponential, which it's okay if that's the absolute best we can do. I have other theoretical courses, especially in AI, where there are a lot of open problems where a lot of the best we can do is exponential time. And maybe there are some small speed ups that we can do in certain situations. But in general, a lot of the problems are still very difficult. But this is not one of them. Parsing is something that we could certainly improve on. So talking about CYK, getting down to that qubit time was great. So we had exhaustive search parsing, which was disgusting. Start with start non-terminal, match each possible non-terminal rule, see if you can generate the target program. That seems like, now that we've seen Turing machines, it kind of seems like start generating programs.
Yeah.
And it generates every possible program, and hopefully it eventually generates your program. It seems like a great approach for a compiler, right? How to turn a compiler into a recursively enumerable process. If there's a syntax error somewhere in your program, the compiler will never finish because it just generates successful program after successful program. It just never generates your program, so it sits on the compilation step for years.
And that'd be really hard to tell.
That'll
tends to
generate my.
Yeah,
my phone.
I was about to say, tell all the guys in Java 1, it's like, well, would you rather have it tell you what's wrong, or would you rather have it spin forever?
That's how base 44 does the phone apps. And that's
So if there were multiple productions for a particular left-hand side non-terminal, then we had to search. We had to either use a depth first search or a breadth first search. If it's a depth first search, then we know it's not necessarily complete because we may never return to be able to explore the other side of that. And if it's breadth first search, then we get that exponential complexity as we branch and branch and branch and branch and branch. It takes twice as long, twice as long, twice as long to explore one production further into the search. So complexity was exponential. We talked about CYK, but we're going to get into LL parsing next time. Not quite yet. We're going to talk about general parsing before we do that. And we looked at LL very briefly, but we're going to start looking at it in much more detail because if a grammar is an LLK grammar, especially if it's an LL1 grammar, then yeah, there are certain types of grammars that can be parsed very, very, very efficiently in linear time rather than cubic time. And that is very exciting. So if you're designing a language or designing a compiler for a language, one of the things you might want to think about is how can I generate LL grammar based off of a particular program? So we're going to talk about parsing kind of at a high level for a bit, and then we're going to dive into the weeds. In general, two main ways you can parse. You can start top down. So this says we start with the start non-terminal and we search through the grammar. This is exactly what we've done so far. Search through the grammar, replacing the start non-terminal with some right-hand side of a production for which the start non-terminal is the left-hand side. With that right-hand side, we're going to expand non-terminals and continue to expand non-terminals until we can intelligently generate the target program. So both exhaustive and CYK and LL are all top-down approaches. The other general approach is bottom-up, where we start with the target program and we're going to look for chunks of that target program that are the right-hand side of some kind of production. And we are going to replace that right-hand side with its non-terminal representation. And the goal of this is to generate the start non-terminal.
Did you say that CYK was the top down?
Yeah.
Yeah, I'm confused. I thought for sure CYK was bottom up. Right, because don't we start with replacing individual?
Yeah, no, you're totally
characters?
right. You're totally right.
Oh, okay.
Yeah,
I was like, oh my gosh, am I gonna fail the homework?
No.
I thought it worked. I thought
sorry. Yeah, you absolutely are right. We're generating aspects of you're taking the string and you're finding ways to substitute those in to eventually generate the start non-terminal. You're absolutely right. I don't mention it here, but CYK is bottom up. So exhaustive is top down, LL is top down, CYK is bottom up, LR is bottom up. And we'll talk about both LL and LR, but I will only ever ask you homework and exam questions on LL because LR is complicated, to say the least. LL is reasonably complicated, but LR is very complicated. And again, we wouldn't use it if we didn't have a reason to. So, example top-down parse. We've done this before. Some kind of leftmost derivation and parse tree. We end up with something like we can go S to A capital B, C. We expand the A. We continue expanding. And at some point, we end up with nothing but terminals. And the fact that we expanded in such a nature, if we do a depth first search through this tree, we end up with A, B, B, C, B, C, which we now have shown is in the language of this grammar. Any questions on how we got there? Again, we just want to show kind of the steps where we expand from the start non-terminal top down, and we eventually generate, we remove all non-terminals and only have terminals left. The leaves of part E here are all terminals, and so a depth first search through this tree generates a string. That string is in the language. The question we haven't really targeted too much is, given that we have a string, how do we intelligently select those productions whenever there are options? That is what LL is going to do. That is the question that we are going to ask with LL. So yes, CYK was bottom up. I feel stupid for saying it was top down. But we haven't really talked about, aside from the exhaustive brute force parsing, a way to start with the start non-terminal and intelligently search, aside from use non-determinism. But we don't have non-deterministic computers, so we need to search. We need to find a way to search in a better than exponential time. For a bottom-up parse, we could use rightmost derivation constructing a tree. So if this were the sequence that we had gone through, which is what we did in the top down, how could we identify it in reverse? We start with the just pieces of this. So we see that B can become capital A, so we're going to replace that. Then an A capital A can become a capital A. And continuing, we just find parts of this that we can continue to replace as we do so to eventually generate the start non-terminal. So it's exactly the opposite order. It's just a matter of where you start and how you search through the space. Are you searching for all possible left-hand sides, which right-hand side? Or are you searching for within the string right now, where is there a right-hand side that I can replace with a left-hand side?
And this grammar has to be unambiguous, right? Could it be ambiguous?
It could be, but it will lead to problems if you do have ambiguity in your grammar. Much better if it does not.
And an approach like this, well, I guess both approaches, right? This would be where having unique identifiable keywords in your language would really help the parser, because those are kind of like landmarks for it to like build the parse tree around it, so to speak, right?
Yeah.
Versus like any expression could be any. I don't know, it's kind of big.
I think I see what you're talking about. Yeah, we will do something like that. And we're gonna start getting into the tools that both LL and LR use for this. The first is surprisingly called first. Didn't see that coming, did we?
Well, I mean, the acronym part, yeah, I thought it was gonna be something like the first is the
It's surprisingly not an acronym, it's just capitalized because it helps us to see that this is a function that's not an actual function name, it is the first function. So first is going to be able to help us when there are multiple possible rules, because we need to be able to, with some small scale search, determine which one of those is going to produce what we want. The question is just, how far ahead do we have to look? So let's say we have some grammar production that says something like, And again, it doesn't matter if this is longer than this, but how far ahead do we have to look into our string to be able to determine which of these productions to apply?
Just one.
One character, if the string starts with an A, is there any reason to look here?
Oh, no.
No. If it starts with a B, is there any reason to look here? No. But you can imagine there might be some ambiguity in this that might say, now can we look ahead one character and determine which one to use? No, we have to start possibly expanding. What if there are 3 different ways for A to expand and 3 different ways for B to expand? Now we have a much harder problem. But if the grammar were designed in such a way that we had a distinct first character like this, then we could very quickly and very intelligently make a selection. We don't need to use non-determinism and go down both paths. We could use some kind of restricted search to more quickly identify which one to do. So we're going to talk about the actual algorithmic process for doing this. And as we talk about the algorithmic process, it doesn't necessarily easily map to how you personally solve those problems. So I recommend both thinking about it in terms of how do you solve a problem like this and how does the computer solve a problem like this? And that way it will make more sense when I go through the algorithmic version. So all first does, we take as input a context-free grammar. And the output is a set of terminals that could be the first terminal of a derived string. So first of when we pass it a terminal is going to be the set that includes itself, and that is it. So we're going to be defining first for every possible terminal, non-terminal, and even possible right-hand side in the grammar. The first of a non-terminal is an iterative process that starts as the empty set, and then we're going to loop through every production for which that non-terminal is the left-hand side and look for the first terminal that can be generated via some sequence of productions starting at that non-terminal. It's kind of the opposite of the CYK process. If at some point in the grammar I see an A, what is the set of possible terminals that could be the next terminal that's generated by some expansion of that A? To give you a sense of what that looks like, let's say we have something weird like this. If we were calculating the first of A, we would see via this production, we could immediately see an A. So this says that it is possible for a string that starts with an A, or the position we are at in the string, if we were at an A right now, that if what's on the stack right now is a capital A, there is an immediate way to generate that. If the character we were at was a B and we still had a capital A, is it possible to generate that first? And the answer is yes. If we take this production that produces a capital B first, and then recursively expand that, we get the B. So we would do something like go from A arrow B A B arrow, that B now becomes B B. And we have a substring here that starts with the character that we are looking for. But if the string started with a C for some reason, and maybe there's something in here that actually expands to a C, then we would see that no, there is no way for these A productions to produce a C first and foremost. But you can see sometimes this is a selective search within the grammar. We actually have to dig into the grammar a bit to be able to find where these first characters could come from. It's not just going to be apparent from the productions that utilize the A on the left-hand side. All right. So the first of a left-hand side defined to be the union of the first of each production on the right-hand side. So if we see first of A, that's going to be the union of every possible first of a right-hand side that A could go to. Which makes sense. In that last case, we had a couple of productions that A could go to. So in order to answer that question, we're going to replace first of A with first of everything that A could immediately derive. This is necessary programmatically. I don't find this to be particularly necessary when you're solving your own problems, because you can just say, looking at this grammar, what are the sequence of terminals, the set of terminals that this non-terminal could expand to, and have that show up first. Then a first of some production is just the first of the first symbol in the right-hand side of that production. So this gets us to an actual process. And here we have some pseudocode that will be very useful when you implement LL parsing for your last project. I'm not necessarily going to go over this immediately because I find that going over the pseudocode is less intuitive than just drawing it out and thinking about how to go through it. But this will be the simplest way to do this when you actually go to code. Yeah.
It's a slide deck.
This is called, it's called parsing. Yeah, it's just called parsing. Slide deck 20. Any other questions about what we are doing? We haven't really gone into any examples yet, but I can certainly clarify what we're doing at this stage. All right, let's go through an example. Here is a very simple grammar. Let's calculate first of S. What are all of the terminals that could be the first terminal in an expansion of the S non-term? Would be another way to state that.
It's A, B, and C.
A, B, and C. We get A from the right-hand side of this. If we can go directly to A, and A can become the first terminals B and C, then there are ways we could say S arrow A, S, B, and then we don't need to expand that any further because we have generated the A from there. S arrow A, arrow B, capital A, that generates the B. S arrow A, arrow C generates the C. So this kind of becomes your proof for the process that you could go through via some sequence of productions to generate A, B, and C. So that is the intuitive version. Let's look at applying the rules from the past slide as a programmatic way of doing this. Because if you're writing this in code, you can't use kind of a larger picture and just look at the grammar and see this. What would the actual rules have you generate? So any questions on this before we go into kind of the programmatic version of it? All right. So first of S is itself, first of S, union, first of the right-hand sides. First of itself starts empty, so we don't need to worry about it. First of any right-hand side that starts with a terminal is going to be that terminal, the set that contains that terminal. Union, the first of a non-terminal, is going to now be replaced with the first of all right-hand sides of that expansion. So we can expand first of A to be itself, which just gives you the empty set. Union, first of something, a right-hand side that starts with a terminal. Union, first of the right-hand side that starts with a terminal. So that gets us B and C. we do the substitution of the set containing B and C for our first of A, and we get empty set union A union B and C to be able to generate A, B, and C. So again, a much more programmatic way of defining this. I find that this programmatic way is only useful if you're writing a program. It's not great for things like solving homework problems. That said, there are possible mistakes that you can make if you're not thorough thinking for yourself in a homework problem. So feel free to use this as a guide. Question?
Also, if obviously like brute force parsing isn't good as a program, sometimes it's good as to solve homework though.
Yeah.
Right, you know,
That's true. For some problems, it can be reasonably efficient. All right, here is another grammar. What is the first of this grammar? First of S for this grammar? B. Just B. If we're getting there programmatically though, we start with itself. First of S, union first of SA, union first of B. And so we get empty set, union empty set. And you see the problem now of self-reference. Where first of S, we can define to start as empty, but the first of SA is going to have us recursively define first of S. And if we do self-reference in this, we just make it the empty set. And the reason is, even if it's gonna generate everything that we already do, but there's no reason, because this answer to this is a set, that if we generate a duplication of that same set, it won't affect the contents of that set. So just redefine if we ever do anything with self-reference, then it is the empty set. And we end up with that. First of S, union first of S, union B. Just gets us B. I said this is going to be getting more challenging at some point, and it seems like this isn't so bad so far. We have not considered grammars with lambda in them, and grammars with lambda make things just a little bit more fun. So we're going to define first of lambda to be lambda. But first of some non-terminal may be able to derive lambda. And if that is the case, then we have to consider the next symbol in the production as well. Because you would have something like, let's give you a very brief example of this. We would have S arrow A, B, A, and A arrow C, C, and A arrow lambda. If we're able to do this, what does first of S generate?
It should be B and CC, because you can
Yes.
have A go to lambda and reach B, but
Right.
we need to have the algorithm to do
Yes.
this as well.
Yes, so basically the fact that this can go to lambda doesn't necessarily mean that identifying first of capital A is enough. We have to add an additional conditional rule that if this can go away in some capacity, then we need to move past it and consider the first of the next element as well. And we can see how here we can generate both strings that start with ABA. If this A becomes a CC, we can generate the C, but if the A goes away, we can generate the B first. So the way we're programmatically going to define that, or to show that, is with this extra rule. And I think I will come back tomorrow and do that, because we are out of time. So we'll get another example with this. I will re-summarize what we have done, and we'll dive into the details of first, and following first, we will have follow.
I thought you were gonna say second.
I tricked you. No. I led you into my trap.
And booze.
There's a trap.
Is that Admiral Akbar in my classroom?
Nuclear Palpatine, we gotta have.
Right. All right, so we'll meet back tomorrow for that. I have office hours in an hour. I can be useful on homework.